In this podcast, I'm going to talk about reaction prediction and do a quick review of the basics that you need before you can do reaction prediction. Reaction prediction refers to being able to write what products will form when you mix certain reactants. Before you can do reaction prediction, you will need to know nomenclature or naming of compounds pretty thoroughly. You will need to know solubility rules and what they imply, and then in the next podcast I'll go over types of reactions. So this podcast is going to be focusing on nomenclature, a quick review of naming compounds from your first year chemistry course, and solubility rules. So let's look over review of naming compounds. Before you can name a compound, you will need to identify the type of compound. For naming purposes, there are three types of compound: ionic, molecular, and acid. Ionic compounds are characterized by the presence of a metal in it, like KCl, K2CO3, PbSO4. All of these are ionic compounds because they have a metal in them. It doesn't matter whether it is a variable valency cation or just a single valency cation. As long as you have a metal in it, it is an ionic compound. A molecular compound is characterized by the absence of a metal, and they are generally liquids and gases, as opposed to ionic compounds, which are generally present as solids. Molecular compounds examples are N2O5, IO3, H2O, and so on. These compounds are characterized by the absence of a metal. And the third type of compounds are acids that begin with H, like HCl, HBr, H2SO4, HNO3, and so on. So to name an ionic compound, what you have to do is you name the metal first, and then you name the anion. With the metal, it can exhibit variable valency. If the metal cation exhibits variable valency, and that list is down here, these are the common cations that exhibit variable valency, and this is a list of polyatomic ions that is must memorize at the AP level. So coming back to ionic compounds, if the cation exhibits variable valency, then you write the lower valency ending in us and higher valency ending in ic. Or you can use a Roman numeral within parentheses to specify the charge on the cation. For example, if it is FeNO3 twice, you know that nitrate has -1 charge, so the charge on iron is 2+, right? So 2+ for iron is lower of the two charges, so it should be iron 2 nitrate, or you can write it as ferrous nitrate. Now, how do you write the formula of an ionic compound if you are given the name? You use a method called as crisscross method, where you put the charges next to each atoms. For example, if you have sodium sulfide and you're asked to write its formula, what you do is you write sodium and you write sulfur. Sodium tends to form +1 cation, sulfur tends to form 2-, and when you crisscross it, what ends up happening is it's Na2S1, and we don't write ones in chem, so it is Na2S. Sodium chloride, on the other hand, is NaCl because it's +1 - 1 charge. So that is how you name ionic compounds. To name a molecular compound, you have two ways again. First name is using prefixes. Prefixes are mono, di, tri, and you look at how many of each you have and then name it accordingly. For example, CO2 is carbon monoxide. Ideally, you'd think it is monocarbon monoxide, but we don't write mono, no mono, before first element. It's a rule. So it's carbon dioxide. The other way of naming this is by writing the oxidation number within parentheses. Please review oxidation numbers so you know how to get oxidation number of carbon, which in this case happens to be 4. You write it within parentheses with Roman numerals. So carbon 4 oxide is the stock way of naming carbon dioxide. To name an acid, you have to again see, does the acid have oxygen in it or not? If oxygen is absent, then the acid is named hydro, ending in ic acid. So hydrochloric acid, hydrobromic acid, hydrofluoric acid. If an acid has oxygen in it, then you end it in ic acid, perchloric acid, perchloric acid, or chlorous acid, and so on. You don't use the word hydro in it. So how do you decide what ending to put here? This ending depends upon the anion that the acid is being formed from. If the end ion ends in ate, then it is ic acid. If the end ion ends in ite, it is us acid. So chlorous acid will be from chlorite. That will be the anion. Now lastly, to name a complex, you name it just like an ionic compound. Cation is named first, followed by anion. Now there can be 3 scenarios. Your cation is a complex, your anion is a complex, or your cation and anion are both complexes. If your cation is a complex, you name it by naming the ligands first, followed by the name of the transition metal cation, and then within parentheses you write its charge, followed by anion name. And the cation, if your complex is an anion, then you name the transition metal's name in 8. We'll discuss this more in detail in later podcasts. Now these are the list of common cations that you must memorize. These are the cations that are transition metal cations and show variable valency. This is a list of must memorize polyatomic ion, and at this point it'll be helpful for you to take a break and try and practice naming these compounds. The answers are given below there, and then you can check your answers. Once you feel confident with the naming, I would suggest that you move to the second part of it, which is solubility rules. When you do reaction prediction, you have to write balanced net ionic equations. To be able to write net ionic equation, the basic question you have to answer is what breaks or dissociates and what remains whole. Now what you can break again varies with the type of compound. Acid and bases have one set of rules and ionic compounds have another set of rules. These are solubility rules for ionic compounds that's on reaction prediction notes. Now here it says always soluble are the compounds which have alkali cations in them, like potassium, sodium ion, rubidium ion, cesium ion, polyatomic cation, or nitrate, chlorate, perchlorate, acetate as anions. What it means is if you have calcium acetate, will it be soluble or insoluble? Well, if there's water present, this will be soluble because all acetates are soluble irrespective of what cation is present. So you can put any cation, it'll still be soluble. Generally solubles are chloride, bromide, iodides, meaning if you put like calcium chloride, it'll be soluble. But the exceptions to solubility are, I call them APH. You know, you have AP courses and honors courses. APH. A for silver, P for lead, and H for mercurous. Remember, it's a lower oxidation states of these ions, APH. So if you had lead chloride, now will that be soluble? No, it'll be insoluble. Generally we write insoluble with a lowercase s and it doesn't dissociate. Similarly for sulfates, soluble except if it is calcium, strontium, barium, or lead. And the way I like to say it is I call them CBS, PBS. Okay, these are the 2 news stations that are fairly easy for you to remember, CBS and PBS. And C is for calcium, B for barium, S for strontium, and P for lead, B for barium, S for strontium. So there's that crossover here, but this helps you memorize. Now I hope you have a good idea to follow these solubility rules. So you can read these and decide which compounds are soluble. Once you know the solubility rules, the third thing that you need to know to build a good foundation for reaction prediction is what actually breaks and what does not break, in addition to ionic compound rules that we just saw. You have to remember that metals are insoluble and are atomic, and they are written just as their atom, like Mg. Now magnesium as a metal is different from magnesium as an ion. Then molecular compounds such as CO2, H2S, they are written as gases and they will not dissociate into ions. So any molecular compounds, you don't break them into ions. Water in pure form does not break. Ionic compounds may or may break depending on solubility rules. And where were the solubility rules? They were down in the same document. If you scroll down, you can see that the solubility rules are given under double replacement reactions. Right here. Okay, let's scroll back up to what you can break and what you can break. Now the next thing is acids and bases. Strong acid and strong bases dissociate. Weak acids and weak bases don't dissociate. Now how would you know whether an acid or base is strong or weak? Well, there is a list that's given here again at the bottom where the solubility rules were given. Just below it, you see strong acids are these 7 acids that dissociate, and every other acid other than that, these 7, is a weak acid, does not dissociate. The strong bases are group 1 bases plus group 2 bases except for beryllium and magnesium. So everything else, meaning in group 1 and group 2, every hydroxide of their metal cations dissociate except for beryllium and magnesium hydroxide. Ammonia is also a common type of weak base that doesn't dissociate. Now let's go back again to what you can break and what you can break. The last couple of things that you need to remember is when you have PS Hofbrinkel, where P stands for phosphorus, S for sulfur, Hofbrinkel for hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. These are diatomic. So what is the implication? When you write, let's say in a reaction, sodium reacts with chlorine, you'll write sodium as Na because it's a metal atom. It can stay by itself, but chlorine does not exist as monatomic atom. It exists as diatomic. So instead of Cl, you will write Cl2. And you'll do the same for hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. But sulfur exists as S8 and phosphorus exists as P4. Lastly, remember the difference between zinc and zinc ion. Do you zinc? You get it. That was my chem joke for you. So zinc and zinc ion and the difference between chlorine and chloride ions. These are the foundations that will help you write good net ionic equations. I will be talking about types of reactions and how to write net ionic equations in the second podcast. Thank you for listening.